Hello, my name is Gerard Barron. I'm the chairman and CEO of the Metals Company. So, availability and sustainability and price are three of the drivers that could really impact the success or otherwise of the transition to a greener future. And the reason is that we know that electric vehicles much more metal intensive. The same with renewable power. And so the question is, where are the metals going to come from? And if we focus on electric vehicles, the average EV will require around 155 kilograms of these four metals: copper, nickel, cobalt, and manganese. So there's some good news and some bad news. The good news is that the metals that are required will be entirely recyclable in the future. But the bad news is that there are other demand drivers. Firstly, there's the transition away from fossil fuels, but the industrialization of the developing world continues. And of course, population growth will continue to put new demand. So we're going to need to mine a whole lot more metals. In fact, if we just focus on electric vehicles and the impact on the production of, say, nickel and copper, only 10% of the mined nickel in 2019 went to batteries, and that's forecast to grow at least 17 times by 2030. And by 2024, both nickel and copper are forecast to be in serious deficit. And geopolitics is also going to play a part here, because if we look on the left-hand side of this graph, it shows the top three producing nations for oil and gas. And we know there have been many battles fought. But on the right-hand side, the top three producing countries for battery metals shows an even greater concentration. And if we look at where America sits, America is nowhere on that battery supply chain today. Yet China, it leads the race, thanks to a very heavy investment program over the last decade. There's also the ESG impacts of metal production today. We've all read about child labor producing cobalt from the Congo, but less spoken about are some of the other land-based mining practices where deforestation, destruction of carbon sinks, the generation of tailings that are created when we process these metals, and lots of NOx and SOx that are released as they're turned into metals. So recently, our company, the Metals Company, published two papers. One of them was a white paper which titled "Where Should Metals for the Green Transition Come From?" And it carried out a full LCA analysis of what if we build 1 billion batteries that are going to be required just for the light transportation fleet from known terrestrial supply lines, or what if we build them from a new source of battery metals in the shape of polymetallic nodules. And the second paper was recently published in the Journal of Cleaner Production, which focused purely on the CO2 impacts. So let's talk about the average EV. We know it requires around 155 kilograms of copper, nickel, cobalt, and manganese. And they happen to be the metals that are found in our polymetallic nodules. But to make that one electric vehicle battery and the copper, we have to use about 10 car parking spaces on land. But along the way, we also have to destroy a lot of biomass, around 560 kilograms. Why? Well, because a lot of that land-based mining is happening in very biodiverse and rich habitats, where we're having to destroy forests and plants and topsoil. And we put at risk around 11 tons of CO2, both by destroying those that biodiverse biomass, and also by not being able to use that land to sequester carbon in the future. And going back to those four metals, they come from very biodiverse habitats on land today. Chile, Indonesia, South Africa, and the Congo lead the production of those four key metals. So Sometimes we know that child labor is still widely used in production of metals, especially in the Congo. And to make that metal for one electric vehicle, if we look at terrestrial metal production, we'd have to touch around 64 tons of metal bearing ore and overburden just to make the metals for that one electric vehicle. And of course, what happens to all of the waste? Well, it gets piled up in places like this. Sometimes it leaks into rivers. Often there are tailings that need to be generated, and they have to be stored forever in tailings dams. And sometimes they don't work so well. This was a picture of a tailings dam burst in Brazil recently, which wiped out many villages and cost hundreds of lives. If we look at where much of the future nickel production is coming from in Indonesia, because of where Indonesia sits on the tectonic plates, it means that you can't build tailings dams. In fact, tailings will either have to be dry stacked, which is very expensive, or, as has been planned, deposited into the deep ocean. So just to make the metals for that one electric vehicle will generate around 13 tons of CO2 emissions, will generate around 64 tons of solid waste, will require around 45,000 liters of water, and will generate 58,000 kilograms of toxic waste material that will have to be kept forever. But of course, we're not building one electric vehicle. The forecast is we'll build at least 1 billion EVs just for light transportation. So that now means 13 gigatons of CO2 emissions and a whole host of waste and toxic tailings and 45 gigatons of water. So I guess the question that we're faced with is, where can we build this inventory of metals, but without that massive ESG footprint? So let's take a step back. If we had our time again and took a planetary perspective, and imagine if we'd come across a resource that didn't require us to tap into our rainforests, to destroy our carbon sinks, but instead we found this large deposit just sat on the surface. And fortunately, that's what we have. That's what we're talking about today at the Metals Company. Imagine if this resource also did not contain any of the nasty elements like mercury and arsenic that generates tailings, but instead this resource contained all of the metals required to power the green transition: high levels of nickel, of copper, of cobalt, and of manganese. And you'll see on this slide, we talk about 32% of the nodule mass is made up of these four metals. But because we don't have any toxic tailings, it means that we don't generate any waste. And that's a real game changer when it comes to the metals industry. Last year, there was around 190 billion tons of waste generated by the terrestrial mining industry. And just to put that in context, municipal waste amounted to around 2 billion tons. So big difference. To make that one electric vehicle, the battery and the copper wiring, instead of having to touch 64 tons of material on land, we'd only have to touch around 6 tons of nodules. And we could massively compress those four indicators. More than 90% of that 13 gigatons of CO2 we could remove, and we'd generate zero waste. We would use only 11% as much water, and we'd eradicate the need for toxic tailings. So these nodules sit in the abyssal zone. It's around 4,000 meters below sea level, an ideal place to put such a large, abundant resource. And we don't need to build fixed infrastructure, because we can essentially build our harvesting systems wherever it makes sense, and we float them on out there, and they're in production soon after. And this is where we are. We're around 1,000 miles off the coast of Mexico. And there's around 1.1 million square kilometers currently under license from the International Seabed Authority. And you can see the area colored in green on this map. The white shaded areas are actually protected zones that the regulator has set aside, areas where no nodules will ever be collected. And so already we have more area in protected zones than there is under exploration licenses. But it's a very large, abundant resource. They estimate there's around 23 billion tons in total in this one large defined area. And the nodules form by precipitating the metals that are in the seawater or that are in the sediment upon which they sit. And they have some very important qualities, including they lie unattached on the ocean floor. So it means that we don't have to drill or blast or dig to find them. They also contain very high grades of these important metals. It's like having 3 tier 1 assets all in one, a world-class nickel, copper, and manganese deposit. We've already established they attain very low levels of arsenic and mercury, so we don't generate tailings. And the grade of the material is very consistent over very large areas. They're pretty small, so they're about the size of a potato, and they're easy to smelt because they're microporous. And there are some economic benefits as well. Because of the very high grade, it means that we can produce these metals in the bottom quartile on the cost curve. So not only tremendous environmental benefits, but also great economic benefits. So it's many of those characteristics that allows us to compress those ESG impacts. So less than 90% less CO2, no solid waste, no toxic tailings, much lower impact on megafauna or biomass, much safer than land-based mining, and also uses only a fraction of the water, doesn't use so much land, so we can put that land to other uses, whether it's food production or sequestering carbon. But of course, we do use seafloor, that's where the nodules are located, and there will be some biodiversity impacts, but we're coming to understand those, and we can also build strategies where we can mitigate those impacts. We'll also use more seafloor. So we estimate around 500,000 square kilometers of seafloor will be required to build those 1 billion batteries. And while that's more seafloor than would be required on land, the biomass impacts are much, much less. In fact, if we look at the average biomass per square meter, there's around 13 grams compared to more than 20,000 grams where we're currently mining much of our nickel and where much of the nickel is forecast to come from. And there is life, of course, mainly megafauna, which are very small organisms, bacteria living in the sediment. And we will disturb those as we pass across them. And to give you a sense of scale, this is a picture of our harvester and our launch and recovery vessel that we're preparing to build. And we worry about the impacts like what happens when we remove the nodules? What happens to the sediment and where do we return the water? But we're in the middle of a very large ocean research program to provide us answers. And what I can say with a very high degree of confidence is that all of those answers are consistent with our belief that we can massively reduce those impacts. We're adopting a very precautionary approach, as is the regulator. There are big set-aside areas, not only from the regulatory, from the International Seabed Authority, but also ourselves. And we're entering this period of trade-offs where we say, of course, there will be some impacts, but those impacts we are coming to understand, and we can see, this is a picture on the right-hand side of an area that almost 30 years ago off the coast of Peru had an industrial plow dragged through it. And 30 years later, you can still see there are some tracks, but that's what they are, they're tracks. On the left-hand side, of course, is a nickel mine in Indonesia, where rehabilitation will not be so easy, and it will take centuries for those areas to regain their purpose. So it's a very innovative approach. It's a very exciting project to be part of, and I think it's something that will play a very important part as we understand how to reduce the impact of producing more metals for our sustainable future.